In every classroom on Earth, gravity is taught the same way. It is a force. Mass pulls on mass, and the bigger the mass, the stronger the pull, and that pull is what holds you to the ground. But here is what they left out. The man who wrote the equation for that pull, Isaac Newton himself, called the idea an absurdity and admitted he could not explain how one object reaches across empty space to grab another. For more than half a century, the planet Mercury drifted off its predicted orbit by 43 arcseconds every 100 years, and no force anyone could find would explain it. And right now, sitting exactly where you are, you cannot feel gravity at all, because there is no force pulling you down. What you feel is the floor pushing up. Nothing in this universe is pulling on anything. Mass is doing something far stranger and far more beautiful, and it has everything to do with the flow of time. Get comfortable. Hit subscribe if you're new here, because by the end of this, the weight in your own legs will mean the opposite of what you have always believed. Now, let's slowly ease into this. Part 1. The most successful wrong idea in history. Gravity is a force. You learnt this as a child, and you have never once had a reason to question it. Mass pulls on mass. The bigger the mass, the stronger the pull. The earth reaches up and tugs on the apple falls, and the whole thing feels as solid and obvious as anything you know. Isaac Newton himself wrote the equation for it more than 300 years ago. And that equation is, without any exaggeration, one of the most successful ideas in the entire history of science. And tonight, slowly and carefully, I am going to show you that it is completely wrong. I want to be precise about what I mean, because this is not a small correction. I am not telling you that Newton was a little off, that he needed to add a decimal place here or a tiny adjustment there. I am telling you that the whole picture, the entire image of mass reaching out across empty space and pulling on other mass, is a fiction. It is a brilliant, useful, magnificent fiction that gives you the right answer about 99% of the time. But it is a fiction nonetheless. And by the time we are finished here, you will not be able to look at a falling object the same way again. You will not want to, because the truth turns out to be stranger, more beautiful, and far more unsettling than anything Newton ever imagined. Before I take the old idea apart, I want to do the opposite. I want to make you comfortable with it. I want to remind you just how extraordinarily good it is, because if you do not first appreciate how strong the building is, you will never appreciate what it means when the foundation underneath it cracks. So let us begin where you began, with something simple. You drop a ball, and it falls. Why? Because the earth has mass, the ball has mass, and there is a force pulling them together. Newton told us exactly what that force is. You take the two masses, you multiply them together, you divide by the square of the distance between their centers, and you put a constant out front. That constant is called the gravitational constant, written as the letter G, and its value is about 6.67 times 10 to the minus 11 in the standard units physicists use. The force of gravity equals G times the first mass times the second mass divided by the distance squared. That little equation is a miracle. I do not mean that as a figure of speech. I mean it as a working, practical fact. With that one line of mathematics, you can predict, to staggering accuracy, where the moon will be next Thursday. You can predict where Jupiter will sit in the sky a century from now. You can predict where a satellite launched from a pad in Florida will arrive 3 days after it leaves the ground. The same handful of symbols that explains why your coffee cup falls off the table also steers spacecraft across billions of kilometers of emptiness and lands them within a few minutes of their predicted arrival. There are very few ideas in all of human thought that reach so far on so little. And the picture that comes with the equation is clean, and it is comforting, and that is part of why it has held on so tightly. In Newton's universe, space is a stage. It is a passive, empty arena, just sitting there, doing nothing. Objects with mass sit on that stage, like marbles set down on a tabletop, and between any two of those objects runs an invisible thread of force, always pulling, always proportional to the masses, always growing weaker as the distance grows. Every object in the universe is connected to every other object by these threads. The Earth pulls on you, and you, in turn, pull on the Earth, though your pull is so small compared to the planets that nobody notices. The whole cosmos is laced together by an invisible web of pulling, and the web obeys a single, simple, elegant rule. You can draw the whole thing on a piece of paper. You can do the calculation in an afternoon with a pencil. Everything makes sense. There are no loose ends, no mysteries, nothing that keeps you up at night. That, more than anything, is the seduction of Newton's gravity. It does not just work, it feels finished. It feels like a question that has been fully and permanently answered, the kind of thing you can teach to a 10-year-old and never have to revisit. For 200 years, that is exactly how the world treated it. I want you to sit inside that comfort for a moment, because we are going to leave it behind, and I want you to feel what we are leaving. Imagine the universe as Newton imagined it. Picture the sun hanging in the middle of the solar system, and the planets strung around it, each one held on its path by an invisible cord of gravity running back to that central fire. Mercury races around on the inside, whipping through its short year. Out past the orbit of Mars, Jupiter rolls slowly through its enormous circuit, and every one of them is held in place by the same simple rule, the same single equation, the same patient pull. It is a clockwork. It is orderly. It is the kind of universe a person can understand and trust. And here is the thing I most want you to hold on to. None of that is going away because the equation failed in practice. The equation does not fail in practice. If you use Newton's gravity to plan a mission to Mars tonight, it will get you to Mars. Engineers still use it, every single day, to build bridges and design harbors and launch rockets, and it works. So, when I tell you the idea is wrong, I am not telling you it is useless. I am telling you something far more disturbing. I am telling you that an idea can be wrong about what is actually happening and still give you the right numbers over and over for centuries with such reliability that no sane person would ever doubt it. The map can be flawless and still be a lie about the territory. Consider how long that trust has held and how many lives have been built on top of it. For more than 300 years, every engineer who ever calculated the swing of a bridge, every navigator who ever plotted a course by the moon, every astronomer who ever predicted an eclipse, and every mission controller who ever guided a spacecraft to another world has reached for Newton's equation and found it waiting, reliable, and exact. Whole generations of brilliant people lived their entire careers inside that equation without ever once finding it wanting. It became less like a theory and more like a fact of nature, as unquestioned as the rising of the sun. When an idea works that perfectly for that long, it stops feeling like an idea at all. It becomes the floor you stand on without thinking, the thing so obviously true that questioning it seems almost childish. And that is exactly the kind of belief that is hardest to give up and most worth examining, because the more certain we are of something, the more startling it is to discover that we had it backward all along. That is the strange situation we are walking into. The most battle-tested, engineering-proven, planet-finding theory in the history of physics describes a universe that does not exist. There are no threads. Nothing reaches across the empty space between the Earth and the falling ball to grab it. The pull you have felt your entire life, the pull that keeps your feet on the floor right now, is not what you think it is. But to understand why, We cannot just be told. We have to watch the old idea earn our trust completely, and then we have to watch it break, crack by crack, exactly the way the people who lived through it watched it break. So, before we tear anything down, let me show you the single greatest triumph this equation ever produced. The moment it found an entire planet that no human eye had ever seen, using nothing but ink, paper, and the assumption that the pull is real. Part 2. The planet found on paper. The story of how we came to trust Newton's gravity so completely runs through a single night in 1846, and it begins with a problem. By the early 1800s, astronomers had been tracking the planet Uranus for decades, and Uranus was misbehaving. It was not following the orbit that Newton's equation predicted for it. The discrepancy was tiny, far too small for any casual observer to notice, but the mathematics of gravity had become so precise by then that even a tiny wobble stood out like a wrong note in a familiar song. Uranus was drifting, sometimes a little ahead of where it should be, sometimes a little behind. The clockwork was slipping. Now, think about the choice the astronomers faced, because it tells you everything about how completely they trusted the equation. They could have concluded that Newton's law was simply wrong out there at the cold edge of the solar system, that gravity behaved differently so far from the sun. That would have been the cautious thing to assume. Instead, they did the opposite. They trusted the equation so completely that they decided the equation could not be the problem. If Uranus was being pulled off course, then something must be pulling it. Something massive, something unseen, something out beyond Uranus that nobody had ever observed. The equation was not broken. The map of the solar system was simply incomplete. Two men set out to find that something, working separately and without knowing how far the other had gotten. In France, there was Urbain Le Verrier, a meticulous and somewhat prickly mathematician who attacked the problem with relentless patience. In England, there was John Couch Adams, younger and quieter, working through the same staggering calculation on his own. The task in front of them was almost absurd. They were trying to work backward from a wobble. They had the symptom, the slight misbehavior of Uranus, and from that alone they had to calculate the mass, the distance, and the exact position in the sky of a planet that no one had ever seen. They were asking the equation to point at empty darkness and tell them precisely where to look. Le Verrier finished his calculation and did something that took real nerve. He did not have a telescope of his own to search with, so he wrote a letter. He sent his prediction to an astronomer named Johann Galle at the observatory in Berlin, telling him, in effect, point your telescope at this exact spot in the constellation of Aquarius, and you will find a new planet. The letter arrived on the 23rd of September, 1846. That same night, Gale and a young assistant turned the telescope to the coordinates Le Verrier had given them, and within a single hour of looking, there it was. A small, faint, blue-green disk, sitting almost exactly where the mathematics said it would be. They had found Neptune. I want you to really feel the strangeness of that achievement, because it is easy to read past it. A planet, a world 4 times the diameter of Earth, drifting through space billions of kilometers away, had been discovered not by an explorer, not by a lucky sweep of a telescope, but by a man doing arithmetic at a desk. Le Verrier never looked through the telescope that found it. He conjured Neptune out of ink and paper and one equation about pulling, and then he told the universe where to produce it, and the universe obeyed. When a piece of mathematics can do that, when it can summon an unseen world from pure calculation, you do not merely accept it, you trust it in your bones. You build your understanding of reality on top of it. And Neptune was not some isolated trick. The same equation was quietly running the whole sky and the whole Earth, getting everything right. Consider the tides. Twice a day, across the entire planet, the oceans rise and fall. Enormous quantities of water lifting and dropping on a steady schedule. Newton's gravity explains it with beautiful simplicity. The moon pulls on the Earth, but it pulls a little harder on the near side, the side facing the moon, than it does on the far side, because the near side is closer and the pull weakens with distance. That difference in pulling stretches the oceans into a slight bulge, and as the Earth rotates beneath that bulge, every coastline passes through high water and low water in turn. With Newton's equation, you can calculate the height of those tides. Engineers designing harbours and bridges and seawalls have been doing exactly that for centuries, and the water arrives, day after day, right on time. Consider the spacecraft we have flung across the solar system. When the Voyager probes travelled to the outer planets, they did not carry enough fuel to make the journey on their own power. Instead, they used the planets themselves. They swung close to Jupiter and then to Saturn, borrowing a tiny sliver of each giant planet's orbital motion, using that borrowed momentum like a slingshot to fling themselves onward, faster and farther, all the way to the edge of the solar system and beyond. Every one of those maneuvers, every precise pass, was planned in advance using Newton's law of gravity. The probes went exactly where the equations said they would go. They are still out there now, in interstellar space, monuments to how well the old idea works. So I need you to understand that this is not some fragile, hand-waving, approximate theory that was always destined to fall apart. This is one of the most rigorously tested ideas in all of science, confirmed by 3 centuries of engineering triumph, by the motion of every planet, by the rise of every tide, by the path of every spacecraft we have ever launched. The picture it paints is satisfying and complete. Space is a passive arena. Masses sit in it like marbles on a table, and between them run invisible threads of force, obeying one clean mathematical law. And the triumphs reach back even further than Neptune, to the very first time Newton's gravity was used to predict the future of the sky. Edmund Halley, a contemporary and friend of Newton, studied the records of bright comets that had appeared over the centuries and noticed that the comet of 1682 followed a path remarkably like comets seen roughly every 76 years before it. Using Newton's brand new law of gravity, Halley proposed that these were not different comets at all, but a single comet returning again and again on a long stretched orbit, pulled around the sun and flung back out into the darkness, over and over, on a fixed schedule. He predicted it would return around the year 1758. Halley did not live to see it. But on Christmas night of 1758, more than 15 years after his death, the comet reappeared, right on time, exactly as the equation said it would. A man had used Newton's gravity to reach decades past his own death, and correctly tell the world when a ball of ice would come back from the edge of the solar system. That is the kind of power we are dealing with, and that is why letting go of it feels almost like a betrayal, which raises the only question that matters. If the theory is this good, this accurate, this thoroughly proven, then where on earth does it go wrong? How can something that finds planets and steers spacecraft and predicts the tides also be, at its very core, a fiction? The answer is that it goes wrong in several different places, and the cracks are subtle. You only see them if you are very careful, very precise, and a little bit obsessive. And the very first crack was one that troubled the man who built the whole thing. It troubled Newton himself, so much that he confessed he found his own greatest idea philosophically impossible to believe. Let me show you what he was afraid of. Part 3. The question Newton could not answer. There is a question hiding inside the simplest fact about gravity, and once you see it, you cannot stop seeing it. The question is this: how does the Earth know the ball is there? It sounds almost childish when you first hear it, the kind of thing a curious 5-year-old might ask before being told to stop asking. But hold it in your mind and turn it over slowly, because it is not childish at all. It is one of the most serious problems in the history of physics, and the man who wrote the equation for gravity knew it. Picture the ball in your hand, and then picture you letting it go. It falls toward the earth. Newton tells you why. There is a force between the ball and the earth, pulling them together. But look closely at the space between them. The ball and the earth are not touching. There is no wire connecting them, no string, no rod, no rope, no physical link of any kind. Between the ball and the ground, there is only empty space, air at most, and below that, nothing. And yet, somehow, across that gap of pure emptiness, the earth reaches out and takes hold of the ball. It grabs it instantly, with no delay, no warning, no signal that travels from one to the other. The pull is simply there, fully formed, the moment the ball exists. Newton had a name for this. He called it action at a distance, one object acting on another, across empty space, with nothing in between to carry the influence. And here is the part most people never learn. Newton hated it. He found it genuinely impossible to believe. He had written the equation, he had proven it worked, he had revolutionized all of science with it, and he still could not bring himself to accept what it seemed to be saying about the world. In a famous letter to a theologian named Richard Bentley, he put it about as bluntly as a person can. The idea that one body could act upon another at a distance, through a vacuum, without anything in between to carry the force, was to him so great an absurdity that he believed no person who was any good at thinking about such matters could ever fall into it. Read that again, and let the strangeness of it land. The man who discovered the law of gravity told the world, in writing, that the most obvious reading of his own law was an absurdity that no competent thinker should accept. He did not know how the pull was transmitted. He had no mechanism. He could not say what the invisible thread between the earth and the ball was actually made of, or how the earth's influence crossed the emptiness to reach the ball at all. He simply found, through his mathematics, that gravity behaved as if such a pull existed, and he was honest enough to admit that he could not explain why. So he did the only thing a careful scientist could do. He published the equation, stated plainly that he was offering no mechanism, and left the deeper problem for future generations to solve. And here is what happened next, and it is a very human thing. Future generations mostly ignored the problem. For 200 years, physicists picked up Newton's equation, used it to get the right answers, and quietly declined to ask the uncomfortable question underneath it. Why bother? The equation worked. It found Neptune. It predicted the tides. It steered the spacecraft. When a tool works that well, the temptation to stop asking what it really means is almost overwhelming. So the question of how the pull crossed the void was set aside, generation after generation, not because anyone had answered it, but because everyone had learned to look away from it. I find something profoundly honest in Newton's discomfort, and I think it is worth pausing on. It would have been so easy for him to declare victory. He had every reason to. Instead, he told the truth about the limits of his own understanding. He knew that getting the right number is not the same as understanding what is happening. He knew that his equation was a description, not an explanation. It told you how strong the pull was, but it said nothing about what the pull was, or how it reached across nothing to do its work. That gap, that silence, at the center of the most successful theory in physics, was the first crack. It was a crack in meaning rather than in numbers, and that is exactly why it was so easy to ignore. The equation still gave perfect answers. It just could not say why. Now, a crack in meaning, on its own, is the kind of thing physicists can live with for a very long time. Philosophers might lose sleep over it, but a working scientist can shrug and say the equation works and move on. If that had been the only problem with Newton's gravity, it might have survived for another 200 years untroubled. A theory does not usually collapse because it fails to explain itself. It collapses when it starts giving wrong answers, when the numbers themselves stop matching the sky. And that is precisely what eventually happened. The philosophical crack was joined by a second kind of crack, a crack you could measure, a tiny, stubborn, persistent error in the heavens that no amount of careful work could explain away. The trouble is, you only find a crack like that if you are looking very closely at exactly the right place. You have to take the most precise measurements you can make of the most carefully studied objects in the sky, and then you have to refuse to look away when the numbers do not quite add up. Most discrepancies in astronomy turn out to be mistakes, or unknown objects, or effects nobody had bothered to calculate. The astronomers who found Neptune had seen a wobble in Uranus and correctly guessed a hidden planet. So when a new and even smaller wobble appeared somewhere else in the solar system, the natural response was to assume the same thing. Somewhere, hidden in the glare, there must be another unseen world doing the pulling. They went looking for it. They were certain they would find it, and this time the universe gave them a very different answer. To find the place where Newton's equation finally cracks in the numbers, we have to travel inward, toward the Sun, to the smallest and fastest of all the planets. We have to look at Mercury, racing around the Sun in the most curved, most extreme region of the entire solar system, and we have to look at a discrepancy so tiny it amounts to about 1/100th of a degree per century. It sounds like nothing. It was everything. It was the loose thread that, when pulled, would unravel the whole comfortable picture of gravity and replace it with something almost no one was prepared to believe. Part 4. The planet that was never there. Mercury is the closest planet to the Sun, and it moves in an ellipse, a stretched circle with the Sun sitting slightly off to one side. That much is ordinary. Every planet moves in an ellipse. But Mercury's ellipse does something subtle and strange. It does not stay still. The long axis of the ellipse, the line running through the point where Mercury comes closest to the Sun, slowly rotates. Year after year, century after century, the whole orbit swings around the Sun like the hand of an enormously lazy clock, the entire elliptical path turning a little further each time around. Astronomers have a name for the point of closest approach to the Sun. They call it the perihelion, and the slow turning of that point is called the precession of the perihelion. Now, most of that precession is no mystery at all. Mercury does not orbit a sun alone in empty space. It orbits a sun surrounded by other planets, and those other planets pull on Mercury too. Venus tugs at it, and Jupiter, with its enormous mass, tugs at it harder, and all the rest add their smaller contributions. Each of those pulls nudges Mercury's orbit a little, and together they make the ellipse precess. Using Newton's equation, you can calculate exactly how much each planet should contribute. You can add it all up and predict the total precession Mercury's orbit should show. This is precisely the kind of calculation the astronomers of the 1800s were superb at. Leverrier, the same man who had found Neptune, did exactly this calculation for Mercury, and the numbers did not add up. When Leverrier carefully accounted for the pull of every known planet, for every effect anyone could think of, he found that his prediction fell short. The observed precession of Mercury was slightly larger than the sum of all the known causes. The gap was about 43 arcseconds per century. I should tell you how small that is, because it is almost comically tiny. An arcsecond is 1/3600th of a single degree. 43 of them per century works out to roughly 1/100th of a degree every 100 years. If you watched Mercury's orbit for your entire lifetime, the unexplained part of the drift would be far too small to see with your eyes. It was a discrepancy buried in the last decimal places of the most careful measurements humanity could make, but it would not go away. That is the thing about a real crack, as opposed to a measurement error. A measurement error wanders. It shows up one decade and vanishes the next. It changes size. It depends on who is holding the telescope. This did not wander. Decade after decade, observation after observation, the 43 arc-seconds sat there, stubborn and persistent and unexplained. Every known cause had been accounted for, and still Mercury moved a little more than it should. Something was pulling on it that the equation could not name. So Leverrier did the obvious thing, the thing that had made him famous. He had found Neptune by assuming an unseen planet was pulling on Uranus. Now he assumed an unseen planet was pulling on Mercury. He proposed a new world, orbiting even closer to the Sun than Mercury itself, hidden in the blinding glare, too small and too close to the Sun to be easily seen. He gave it a name. He called it Vulcan, after the Roman god of fire, which seemed fitting for a planet roasting in the Sun's furnace. And the search for Vulcan began. For half a century, astronomers hunted for Vulcan. This was not a half-hearted effort. Finding it would have been another Neptune, another triumph for Newton's gravity, another planet conjured from a discrepancy. Observers waited for total solar eclipses, those rare moments when the moon blocks the sun's blinding face and the sky goes dark in the middle of the day, because only then might a faint planet hiding close to the sun become visible against the briefly darkened sky. Expeditions were organized and sent to the path of totality. Telescopes were aimed at the edge of the hidden sun. Claims came in. Someone would announce that they had seen it, a small dark dot crossing the sun's face, and excitement would build, and then the sighting could not be confirmed, and the claim would quietly collapse. Again and again Vulcan was reported, and then retracted, glimpsed and then lost. It was never found. Let me say that plainly, because it is the whole point. There is no planet Vulcan. It does not exist. There is no hidden world orbiting between Mercury and the Sun, and there never was. Half a century of searching turned up nothing, because there was nothing to find. The 43 arc-seconds were real, but the explanation everyone reached for was a phantom. And this is where the story of Mercury becomes something more than a footnote. The strategy that had worked so perfectly for Uranus, the strategy of trusting the equation and blaming a hidden mass, failed completely for Mercury. The same brilliant move, made by the same brilliant man, came up empty. That failure is the real crack, and it is so much more serious than it first appears. When the Neptune strategy works, it confirms the equation. When it fails, it points a quiet finger of suspicion back at the equation itself. Maybe the reason no one could find the missing mass was that there was no missing mass. Maybe the problem was not a hidden planet pulling a little extra. Maybe the problem was that Newton's law of gravity, the equation that found Neptune and steered the voyagers and predicted the tides, was very slightly, very subtly wrong, precisely in the place where gravity is strongest, closest to the Sun, where Mercury races through the most curved region of the whole solar system. Maybe the equation that worked everywhere else broke down exactly there, in the extreme, where the effects it got wrong were finally large enough to measure. It is worth pausing on how strange the search for Vulcan became, because it shows how badly people wanted the old answer to hold. There were respected astronomers who became convinced they had seen the planet. A French doctor and amateur observer named Edmond Lescarbot reported watching a small dark dot cross the face of the Sun in 1859, and Leverrier himself, delighted, travelled to meet him, examined his modest equipment, and announced that Vulcan was real. Other sightings followed over the years, each one stirring excitement, each one eventually fading under scrutiny, contradicted by other observers who had been watching the same sun at the same time and seen nothing. The pattern repeated for decades: a sighting, an announcement, a wave of hope, and then silence as the evidence dissolved. People were not lying. They were looking at the sun, which is a difficult and dangerous thing to observe, and they were seeing sunspots and stray reflections and small flaws in their instruments, and their longing for the missing planet filled in the rest. The harder everyone searched for Vulcan, the more clearly its absence pointed at a truth nobody wanted to face. Most physicists were not ready to think that thought. The equation had earned too much trust. It seemed far more likely that some small effect had been overlooked, some subtle pull miscalculated, than that Newton himself had been wrong. So the 43 arcseconds sat there, unexplained, a tiny splinter lodged in the foundation of physics, waiting. It would sit there for decades. And the person who finally pulled it out would not do it by finding a missing planet, or by correcting a calculation, or by looking harder at Mercury at all. He would do it by reaching all the way down to the nature of space and time themselves, and by realizing that a second, deeper crack had been quietly waiting in Newton's gravity the entire time. A crack that had nothing to do with planets and everything to do with the speed of light. Part 5. The crack that came from a patent office. The second crack in Newton's gravity did not come from the sky. It came from a young man sitting at a desk in a patent office in Switzerland, thinking about light. The year was 1905, and the young man was Albert Einstein, who at that point was not a famous professor, but a junior clerk reviewing patent applications, doing his real physics in the margins of his day. That year he published a theory that would come to be called special relativity, and although it was not about gravity at all, it quietly drove a knife straight into the core of Newton's law. The central idea of special relativity is simple to state and almost impossible to fully absorb. Nothing can travel faster than the speed of light. Not matter, not energy, not any signal, not any form of information or influence whatsoever. The speed of light is not just the speed that light happens to travel. It is a fundamental limit woven into the structure of reality itself, a cosmic speed limit that nothing in the universe can exceed. Light moves at about 300,000 kilometers per second, and that number is not merely fast. It is the absolute ceiling on how quickly any cause can produce any effect anywhere in the cosmos. If something happens here, the news of that happening cannot reach there any faster than light can carry it. Now hold that idea up next to Newton's gravity and watch what happens, because the two cannot both be true. In Newton's universe, gravity acts instantaneously. The pull between two masses is simply there, fully formed, the moment the masses exist, no matter how far apart they are. And that means a change in gravity would also be instantaneous. Let me make this concrete with a thought experiment that physicists love, because it exposes the problem so cleanly. Imagine that the sun, right now, suddenly vanished. Not dimmed, not exploded, simply gone, erased from existence in an instant. What would happen to the Earth? In Newton's universe, the answer is immediate and absolute. The moment the sun disappears, its gravitational pull disappears with it, everywhere, all at once. The Earth, no longer held on its curved path, would instantly feel the absence of that pull and fly off in a straight line into the dark. There would be no delay, no transition, no waiting. The gravitational field of the entire solar system would readjust itself in the same instant, across billions of kilometers, faster than any signal could possibly travel. The information that the sun was gone would arrive everywhere simultaneously, the moment it happened. But special relativity says this is impossible. The information that the sun has vanished cannot travel faster than light, and light from the sun takes about 8 minutes to reach the Earth. So if the sun disappeared, you would not know it for 8 minutes. You would continue to see the sun shining in the sky, light that left it before it vanished, still arriving on schedule. And here is the part that breaks Newton. During those same 8 minutes, the Earth would continue to orbit. It would keep curving along its path around a sun that no longer exists, because the change in the gravitational field cannot have reached us yet. For 8 full minutes, the Earth would faithfully circle a ghost. Only after the light went dark would the pull also vanish, and only then would the Earth sail off into space. Newton's gravity does not allow for those 8 minutes. It demands that the Earth react instantly, and that demand violates the deepest law special relativity had just uncovered, the law that nothing outruns light. This is not a small technicality. This is not a rounding error in the 14th decimal place. This is a structural failure, a head-on collision between two theories that cannot both describe the same universe. Newton's gravity requires instantaneous action across any distance. Special relativity forbids any action from crossing distance faster than light. One of them has to be wrong, and special relativity was built on experimental grounds so solid that it was not going to be the one to fall. So now, stack the problems up and look at them together, because by the early 1900s, the situation had become genuinely serious. The equation gives the wrong answer for Mercury, off by 43 arcseconds per century that no missing planet can explain. The theory provides no mechanism whatsoever for how the pull crosses empty space, a gap Newton himself confessed he found absurd. And now the theory demands that gravity act instantaneously, in flat violation of the cosmic speed limit that all the rest of physics had come to accept. 3 strikes. A wrong number, a missing mechanism, and a fundamental contradiction with the speed of light. The comfortable, complete, clockwork picture of gravity was not so complete after all. And yet, notice what no one could do. No one could simply throw Newton's gravity away, because it still got the right answer almost every single time. That is the agonizing situation that physics found itself in. You had a theory that was clearly, demonstrably broken at its foundations, and you could not replace it, because nothing else came anywhere close to matching its accuracy. You cannot abandon a tool that finds planets and steers spacecraft just because it has philosophical problems and a tiny error in Mercury's orbit. You need something better, something that keeps every one of Newton's spectacular successes while fixing every one of his failures. And nobody had the faintest idea what such a theory could even look like. The breakthrough, when it finally came, did not come from staring harder at planets or at the speed of light. It came from a daydream. It came from Einstein, a few years after special relativity, sitting and imagining something so simple that it sounds like a child's puzzle. He imagined a man falling. He imagined what that falling man would feel. And in that ordinary image, the experience of falling, Einstein found the thread that, when he pulled it, would unravel 200 years of certainty about what gravity is. He would later call it the happiest thought of his life. To understand it, I need to take you out of the solar system entirely. I need to put you inside a sealed box, floating in the dark, far from everything, and ask you a question that has no easy answer. Part 6. The Box. I want to put you somewhere, and I want you to come with me and really inhabit it, because this single thought experiment is the hinge on which the whole story turns. Forget the planets for now. Forget the sun and Mercury and the tides. I am going to seal you inside a box. You are inside a sealed box. It has no windows, no instruments pointed outward, no way of any kind to see what lies beyond its walls. You are floating somewhere far out in space, far from any star, any planet, any galaxy, in a region as empty as anywhere in the universe. And you are weightless. You drift in the middle of the box, turning slowly. Your water bottle hangs in the air beside you, motionless. Your shoe, which slipped off your foot, floats near your shoulder. You give the wall a gentle push with one finger, and you drift slowly across the empty space and bump softly into the opposite wall. There is no up here, and there is no down. Every direction is the same as every other. Nothing falls, because there is nothing to fall toward. This is pure, undisturbed weightlessness, and it feels exactly like the footage you have seen of astronauts adrift inside their spacecraft. Now, without telling you, I bolt a powerful rocket to the bottom of your box, and I ignite it. The rocket begins to push the box forward, accelerating it in the direction your feet are pointing, at a very particular rate. It pushes the box faster and faster, gaining 9.8 meters per second of speed with every second that passes. And inside the box, your whole world changes. You feel yourself settle. You drift down toward what is now unmistakably the floor, and your feet touch it, and you are standing. You feel heavy. Your water bottle, which had been floating, drops and lands on the floor. Your shoe falls. You take a coin from your pocket and let it go, and it falls and clinks against the floor at your feet. You feel the firm pressure of the floor against your soles, holding you up. Everything in the box now behaves exactly as it would in your living room at home. And here is the question Einstein asked, the question that changed everything. Can you tell the difference? Locked inside that windowless box with no way to see out, is there any experiment you could possibly perform that would tell you whether the rocket is accelerating you upward through empty space, or whether your box is simply sitting at rest on the surface of the Earth? With the planet's gravity pulling you down, you feel weight pressing on your feet in both cases. You drop objects and they fall to the floor in both cases. You set a pendulum swinging and it swings in both cases. You measure how fast a dropped object accelerates and you find 9.8 meters per second squared in both cases. You can measure more and more precisely. You can try every experiment you can devise, and you will never find a difference. There is no test, none, that can distinguish the pull of gravity from the push of acceleration. Einstein's answer was bold and total. He did not say the two situations are similar. He did not say they are merely hard to tell apart. He said they are physically identical. Being pulled down by gravity and being accelerated upward through space are not two different things that happen to feel the same. They are, in the deepest physical sense, the same thing. He called this the equivalence principle, and he later said that the moment he grasped it was the happiest thought of his life. It looks at first like a modest little observation about boxes and rockets. It is, in fact, a crack in the foundation of reality, and through that crack, a completely new picture of gravity would come pouring out, because hidden inside that simple equivalence is a question nobody had bothered to ask for 200 years, a question whose answer had always seemed too obvious to be interesting. Why does everything fall at the same rate? You have known this fact since you were a child. Galileo demonstrated it around the year 1590. Take a heavy rock and a light rock, lift them to the same height, and drop them together, and they hit the ground at the same instant. Ignore the air, which slows a feather but not a cannonball, and a feather and a cannonball fall side by side at precisely the same rate. Drop a marble and a boulder from a tower, and they land together. Everyone knows this. It is one of the first things you learn about how the world works. But have you ever stopped to ask why? Why should a heavy thing and a light thing fall at the same rate? It is genuinely strange when you think about it, and Newton's own equation makes it stranger. In Newton's law, the force of gravity on an object is proportional to its mass. A heavier object feels a stronger pull, so a boulder is pulled toward the earth much harder than a marble is. If a stronger pull were the whole story, the boulder should fall faster. But it does not, and the reason it does not is that the very same heavier object is also harder to move. It has more inertia, more resistance to being accelerated by any force at all. The boulder feels a stronger pull, but it also resists that pull more stubbornly, and the two effects cancel out exactly. The extra pull and the extra resistance balance so perfectly that the boulder and the marble fall at identical rates. Try, for a moment, to actually be the person in the box, hunting for the difference, because the harder you try, the more the wall closes in. You weigh yourself on a scale, and the scale reads the same whether the rocket is firing or the box rests on Earth. You build a careful pendulum and time its swing, and it swings identically in both cases. You drop two different objects, a heavy wrench and a light pen, and they fall and land together, in both cases, exactly as Galileo promised. You measure the way a beam of light behaves, the way a gyroscope holds its spin, the way a flame burns, and every single experiment gives you the same reading in the accelerating box as it would on the surface of the planet. There is no clever trick left, no last hidden test, no instrument sensitive enough to catch a difference, because there is no difference to catch. This is the part people find hardest to accept. It is not that telling gravity from acceleration is difficult. It is that the two are, at the level of physics itself, the very same phenomenon wearing two different stories. Sit with how suspicious that is. Two completely different properties of an object are involved here. One is how strongly gravity pulls on it, which physicists call its gravitational mass. The other is how hard it is to push or accelerate, which they call its inertial mass. There is no obvious reason in the world why these two numbers should be the same. One is about how the object responds to gravity, the other is about how it responds to any force at all. They are, on the face of it, unrelated properties. The way a thing's colour is unrelated to its loudness. And yet, for every object ever tested, they come out exactly equal. The charge that makes gravity pull on you and the stubbornness that resists being shoved are, as far as anyone can measure, the very same quantity. In Newton's theory, this is a coincidence. A perfect, universal, suspiciously exact coincidence that the theory never explains. And Einstein, staring at his box, became convinced it was not a coincidence at all. Part 7. The Thread He Pulled. Einstein was the kind of mind that, upon finding a loose thread, could not stop pulling until the entire garment came apart in his hands. The loose thread here was that suspicious coincidence, the perfect equality between how strongly gravity pulls on a thing and how stubbornly that thing resists being moved. Let me show you, step by step, how pulling on that one thread unravels the whole idea of gravity as a force. Start with the equivalence principle, the thing we established inside the box. Gravity and acceleration are physically identical. Now ask what that implies about falling. Picture yourself back inside the box, but this time the box is sitting on the surface of the Earth, and you let go of a ball. The ball falls to the floor. But the equivalence principle says this situation is identical to the box accelerating upward through empty space with no gravity at all. So picture that version instead. Out in open space, the rocket fires, the box accelerates upward, and you let go of a ball. What happens to the ball? Nothing happens to the ball. The instant you release it, no rocket is bolted to the ball. There is no force on it whatsoever. It simply hangs there in space, motionless, exactly where you let it go. It is the floor of the box, driven by the rocket, that rushes up to meet the ball. The ball is not falling. The floor is rising. Now bring that insight back to Earth, because the equivalence principle says the two cases are the same. When you drop a ball in your living room and watch it fall, the truthful description, the one that matches the open space version, is that the ball is not being pulled down at all. The ball is simply sitting there, doing nothing, perfectly free, while the floor rushes up to meet it. That sounds insane. The floor is not moving. The Earth is not expanding. And yet the equivalence principle insists that the falling ball and the floating ball with a rising floor are the same physical situation. Something has to give. Either the equivalence principle is wrong, or our most basic idea of what falling means is wrong. Einstein bet on the second. And here is where the suspicious coincidence finally gets explained beautifully and completely. Remember the puzzle. Why does every object fall at the same rate, regardless of its mass? In Newton's picture, there is no reason for it, just that perfect, unexplained cancellation between pull and resistance. But now, suppose the ball is not being pulled at all. Suppose falling is not the result of a force acting on the object. Suppose, instead, that a falling object is simply coasting freely, following the natural path laid out by the shape of space and time around the Earth. If that is what falling is, then the mass of the falling object does not matter, because no force is acting on it that would need to overcome its resistance. A heavy ball and a light ball follow the same path for the same reason that two cars coasting down the same hill follow the same road. The road does not care how heavy the car is. The path is a property of the road, not of the traveller. That is the resolution, and it is the hallmark of a correct idea. In Newton's theory, the equality of gravitational and inertial mass is a miraculous coincidence with no explanation. In Einstein's emerging picture, it is not a coincidence at all. It is inevitable. It could not be otherwise. If gravity is not a force pulling on objects, but is instead the shape of the space and time that objects move through, then of course everything falls the same way, because everything is following the same shape. The lead ball and the wooden ball trace identical paths because the path belongs to the geometry, and the geometry does not know or care what the falling object is made of. A puzzle that had sat unexplained for 2 centuries dissolves the instant you stop thinking of gravity as a pull and start thinking of it as a shape. I want to dwell on how powerful that move is, because it is easy to rush past it. A good scientific theory does more than predict the right numbers. The very best theories take things that the old theory had to accept as brute, unexplained coincidences and reveal them as necessary consequences, things that simply had to be true. Newton could measure that gravitational and inertial mass were equal, but he could never say why, and he never tried. Einstein's idea forced them to be equal, automatically, as a side effect of what gravity fundamentally is. When a new theory takes one of the deepest unexplained accidents of the old picture and turns it into something obvious and necessary, that is the signal that you have found something true. You have not just fit the data better. You have understood something the old theory never could. How precisely equal are these two masses, by the way? Because this is the kind of claim you can test, and physicists have tested it with almost obsessive care. Around the year 1906, a Hungarian physicist named Loránd Eötvös built an exquisitely sensitive instrument, a torsion balance, designed to detect any difference at all between gravitational and inertial mass. He found them identical to within a few parts in 100 million. Since then, the tests have only grown more refined. Experiments bouncing laser beams off reflectors left on the moon have pushed the agreement far further. A dedicated satellite experiment, carried out in the years around 2020, confirmed the equality to better than 1 part in 1,000 trillion. Two properties that have no obvious reason to be related turn out to be identical to 15 decimal places. That is not the signature of a coincidence. That is the signature of a single underlying truth wearing 2 different names. So the thread, fully pulled, has led somewhere astonishing. Falling is not being pulled. Falling is coasting freely along the natural shape of space and time. The reason everything falls together is that everything follows the same shape. And the perfect equality of the two masses, the coincidence Newton could only shrug at, is no coincidence at all, but a guarantee built into the very nature of gravity. But a good idea has to do more than tidy up old puzzles. It has to stick its neck out. It has to predict something new, something Newton's theory flatly forbids, something you can go out and check. And Einstein's idea did exactly that. It made a prediction so bold that, when it was confirmed, it turned an unknown physicist into the most famous person on Earth. The prediction was about light, and to see why, we have to go back inside the box one more time. Part 8. Light must bend. Step back into the accelerating box, the one floating far out in space with the rocket firing beneath it. This time, I want you to mount a small laser on the left wall, pointed straight across the box, perfectly horizontal, aimed at a target on the right wall. You switch it on, and a thin beam of light shoots across the box from left to right. Now ask a careful question. Where does the beam land on the right wall? Look at it first from the outside, from the point of view of someone floating motionless in space, watching your box accelerate past them. To that outside observer, the light does the simplest thing imaginable. It travels in a perfectly straight line, as light always does. It leaves the left wall and crosses toward the right wall in a dead straight path. But here is the thing. While the light is crossing, the box is accelerating upward. In the tiny sliver of time it takes the beam to travel from one wall to the other, the whole box, walls and floor, and you, has moved up a little. So the beam, which left the left wall at a certain height, arrives at the right wall when the right wall has risen slightly. From the outside, the light went straight, but the box slid up underneath it. Now go back inside the box, where you are standing, watching your own laser. From your point of view, sealed inside, you do not feel like you are accelerating. You feel like you are standing still in gravity, exactly as the equivalence principle promised. So from inside, what you see is this. The light leaves the left wall at a certain height, and it arrives at the right wall slightly lower than where it started. The beam, to you, curved downward on its way across the box. It bent toward the floor. And since you cannot tell the difference between this accelerating box and a box sitting still on Earth, the conclusion is unavoidable. If acceleration bends light, and acceleration is identical to gravity, then gravity must bend light too. Now feel how radical that conclusion is, because in Newton's world it is simply forbidden. Light, as far as Newton's gravity is concerned, has no mass. And in Newton's equation, the force of gravity is proportional to the masses involved. If one of the masses is zero, the force is zero, because 0 times anything is 0. So Newton's law says, flatly, that gravity cannot touch light. A beam of light should pass through a gravitational field utterly undisturbed, like a ghost walking through a wall, bending for nothing and no one. Einstein's idea says the exact opposite. Light bends. A ray of light passing near a massive object will be deflected, its path curved by the gravity it passes through. The two theories do not merely differ in emphasis here. They make flatly contradictory predictions. Newton says 0. Einstein says a specific, calculable, non-zero amount. And that means you can settle it. You can go out into the world and look, and the universe will tell you which man was right. There is no more massive object near us than the sun, so the sun is where you would look. If Einstein was right, then starlight passing close to the edge of the sun, on its way to Earth, should be bent slightly as it grazes that enormous mass, which would make the stars near the sun's edge appear shifted, nudged outward from their true positions. The trouble is, you cannot normally see stars near the sun, because the sun's blinding light washes them out completely. There is exactly one circumstance in which the sky right next to the sun goes dark enough to see the stars behind it: a total solar eclipse. In 1919, a British astronomer named Arthur Eddington set out to catch one. He organised 2 expeditions to observe a total eclipse of the sun, sending one team to the island of Principe off the west coast of Africa and another to the town of Sobral in northern Brazil, so that if clouds ruined one sight, the other might still succeed. The plan was demanding and delicate. During the few minutes of totality, when the moon slid fully across the sun and the day briefly turned to twilight, the astronomers would photograph the stars that appeared close to the darkened sun. Then they would compare those positions to where the same stars sat in the night sky months later, when the sun was nowhere near them. If the starlight had been bent by the sun's gravity on its way past, the stars near the sun would appear shifted outward, and the size of that shift would tell them whether Newton or Einstein had described the universe correctly. Picture the moment of the eclipse itself. The light fades in the middle of the day, the temperature drops. The sun's outer atmosphere, its pearly corona, flares out around the black disk of the moon. The astronomers work quickly and silently, swapping photographic plates, exposing image after image of the brief, impossible darkness, the stars of the daytime sky glittering for a few minutes around the hidden sun. And on those fragile glass plates, captured in those stolen minutes, was the answer to a question that had stood for over 200 years. Did the starlight bend, and if so, by how much? It bent. When Eddington and his colleagues measured the plates and compared the star positions, the stars near the sun had shifted outward, and the size of the shift matched Einstein's prediction, not Newton's. The sun's gravity had bent the path of light passing by it, by very nearly the exact amount Einstein's theory demanded, and by twice the amount that even a naive attempt to apply Newton's gravity to light would have given. Newton was wrong. After 2 centuries, as the unquestioned law of the cosmos, the old theory had been beaten by a measurement of starlight during an eclipse. I want you to appreciate how fragile the whole thing was, because it makes the result more extraordinary, not less. These expeditions depended on a few minutes of perfect weather on a specific day, in remote places, thousands of kilometers from home, with delicate glass photographic plates and telescopes that had to be hauled across oceans and set up in the heat. At Sobral, the skies cooperated. At Principe, where Eddington himself was stationed, clouds threatened to ruin everything, and for most of the eclipse, the sun was hidden. Only in the final moments did the clouds thin enough for him to capture a handful of usable images through gaps in the overcast. The measurements that overturned 2 centuries of physics came down to a small number of photographs taken in stolen seconds of clear sky, of stars barely visible beside a blacked-out sun, their positions shifted by an amount smaller than you could see without careful instruments. When the results were announced months later at a joint meeting of Britain's leading scientific societies, the chairman called it one of the greatest achievements in the history of human thought, made in the very theatre where a portrait of Newton hung on the wall. The world responded as if a spell had broken. Newspapers across the globe carried the news that a theory which had reigned for over 200 years had been overturned by a young physicist almost no one outside of science had heard of. Einstein became famous overnight, the most celebrated scientist on the planet, his name suddenly known in households that could not have explained a single equation he had written. The bending of starlight made for sensational headlines, and it deserved them. But the headlines told only part of the story. The most profound confirmation of Einstein's theory had actually arrived 4 years earlier, quietly, in Einstein's own study, with no newspapers and no eclipse. It had to do with a number we have already met: 43 arcseconds per century in the orbit of Mercury. Part 9. The number that made his pulse race. In November of 1915, after nearly a decade of struggle, Einstein arrived at the final form of the equations that describe how gravity really works. These are called the Einstein field equations, and we will look at what they say a little later. For now, what matters is what he did the moment he had them. He took his brand new theory of gravity, the theory in which mass bends space and time rather than pulling on things, and he turned it on the one problem that had defeated everyone for over half a century. He used it to calculate the orbit of Mercury. Remember where that problem stood. Mercury's orbit precessed by about 43 arcseconds per century, more than every known cause could explain. The hidden planet Vulcan had been hunted for 50 years and never found, because it did not exist. The discrepancy had become a quiet, permanent embarrassment, a tiny wrongness sitting at the center of the solar system that nobody could account for. Einstein's new theory predicted that gravity would behave slightly differently from Newton's law in regions where gravity is very strong, and there is no stronger gravity in the solar system than right next to the Sun, where Mercury, the innermost planet, races through the most curved region of space and time we have. If anywhere would show the difference between Newton and Einstein, it would be Mercury. So Einstein did the calculation. He worked through what his theory predicted for the extra precession of Mercury's orbit, the part that Newton's gravity could not produce. And the answer came out to 43 arcseconds per century. Not roughly 43, not approximately, not in the right ballpark, not close enough to be encouraging, exactly 43. The precise number that astronomers had measured and puzzled over for more than 50 years fell straight out of his new equations, naturally, with nothing forced and nothing adjusted to make it fit. The discrepancy that had haunted physics for half a century simply dropped out of the mathematics, as cleanly and inevitably as a ball drops from your open hand. I want you to imagine that moment, because it is one of the most intensely human moments in the history of science, and it happened not in a laboratory, but at a desk, alone. Einstein is sitting with his calculation in front of him. He has been working toward this theory for almost 10 years, through failures and dead ends and equations that collapsed under their own weight. And now he runs the numbers on Mercury, a test he did not design and cannot fudge, because the measured value has been sitting in the astronomy books for decades, waiting. The number comes out, 43, it matches. And in that instant, before any eclipse, before any newspaper, before the rest of the world had the faintest idea, Einstein knows. He knows, with a certainty that goes past anything a single experiment could give him, that he has found how the universe actually works. He later described what that moment did to him in physical terms. He wrote that when he saw the result, his pulse raced and something inside him seemed to give way. He said he was beside himself with excitement for days afterward. This is a man not generally given to dramatics about his own work, and he is telling us that a column of arithmetic about a planet's orbit left him shaking for days. That is what it feels like to see, for the first time, that your strange idea is not just elegant but true, that the universe has quietly confirmed it without being asked. The bending of starlight, 4 years later, would make him famous. But Mercury was the moment he knew, and he knew it in private, with no audience, holding nothing but a piece of paper that agreed with the sky. Let me tell you what his theory was actually saying about Mercury, because it is lovely once you see it. In Newton's picture, the space around the Sun is just empty stage, and Mercury traces a fixed ellipse through it. In Einstein's picture, the Sun's enormous mass bends the space and time around it, and the geometry near the Sun is slightly different from the flat geometry Newton assumed. Mercury, closer to the Sun than any other planet, moves through the most strongly curved region of all. And, in that curved geometry, the straightest path Mercury can follow is not quite a closed ellipse. It is an ellipse that fails to perfectly close, that shifts a little with each orbit, so that the whole path slowly rotates around the Sun. The 43 arcseconds were never the pull of a hidden planet. They were the signature of curved space-time, written into the orbit of the nearest planet to our star, waiting half a century for someone to read them correctly. So consider what Einstein's theory had now done before it was even fully famous. It had taken the philosophical crack, the absurdity of action at a distance, and healed it, because in the new picture nothing reaches across empty space at all. It had taken the contradiction with the speed of light and resolved it, because changes in gravity, as we will see, propagate at the speed of light rather than instantly, and it had taken the measured crack, the stubborn 43 arcseconds of Mercury, and explained it exactly on the first try with no adjustment. One idea, the idea that mass bends space and time, had closed all 3 wounds in Newton's gravity at once. That is not how a lucky guess behaves. That is how the truth behaves. There is something I want you to notice about the order in which this happened, because it tells you something true about how knowledge actually works. Einstein did not invent his theory to explain Mercury. He built it for entirely different reasons, out of the equivalence principle and the demand that gravity respect the speed of light, working from first principles rather than from any single stubborn measurement. The 43 arcseconds were not the goal. They were a test the theory had to pass, a number sitting in the astronomy books that he had no power to change. When a theory built for one set of reasons turns around and correctly predicts a completely separate fact it was never designed to address, that is the strongest signal in all of science that you have touched something real. A theory tuned to fit one measurement can always be suspected of being rigged. A theory that explains a measurement it was never aiming at cannot. Mercury was not a target Einstein hit. It was a target that was already there, waiting, and his theory walked straight into it without trying. And yet, for all of that, I still have not told you the central idea. I have shown you that Newton's picture fails, and that Einstein's picture succeeds, and that gravity must be the bending of space and time, rather than a force of pulling. But I have not yet told you what that bending really is, or why mass causes it, or what it means to say that space and time can curve. I have spent all this time carefully taking the old building apart. Now, I want to show you the new one because it is the most beautiful structure in all of physics, and at its center is something that sounds, the first time you hear it, completely impossible. Mass does not pull. Mass warps time, and the slowing of time is the thing you have been calling gravity your entire life. Part 10. Mass warps time. Forget pulling. Forget invisible threads stretching across the void. Forget action at a distance. Forget forces reaching out to grab. Let all of it go, because here is what is actually happening, and it is stranger than any of it. Mass warps time. Not as a metaphor, not as a figure of speech, but literally, physically, measurably. The presence of mass changes the rate at which time itself flows. The actual ticking of seconds, the pace at which the future arrives, runs at different speeds in different places, depending on how much mass is nearby. And that difference, that slope in the flow of time, is the thing you have been calling gravity. Let me prove it to you with the most precise instruments humans have ever built. Take two identical atomic clocks so accurate they would not gain or lose a single second in hundreds of millions of years. Place one of them on the floor of a room and place the other on a shelf near the ceiling, a meter or two higher up. Now wait. You do not even have to wait very long. After a few days, if your clocks are good enough, you will find that they no longer agree. The clock on the floor has fallen behind. It reads a slightly earlier time than the clock near the ceiling. The two clocks, identical in every way, sitting in the same room, have ticked at different rates. The difference is unimaginably small, measured in femtoseconds, a femtosecond being 1/1,000,000 of 1/1000,000,000 of a second. But it is real, and it is repeatable, and it is not a flaw in the clocks. The clocks are working perfectly. They disagree because time itself is running at different rates at the two heights. Closer to the Earth, deeper in the planet's gravity, time runs slightly slower. Farther from the Earth, higher up, time runs slightly faster. The clock on the floor is not broken. It is simply sitting where time flows more slowly, and so it honestly records fewer seconds than its twin near the ceiling. This is not science fiction, and it is not theory waiting for proof. It has been measured again and again with better and better instruments, and the measurements always agree with Einstein. The first time anyone caught this effect directly was in 1959, in an experiment by two physicists named Robert Pound and Glenn Rebka at Harvard. They did not have atomic clocks accurate enough for the floor and ceiling test, so they used something cleverer. They sent a beam of gamma rays, a very pure form of light, straight up a tower about 22 meters tall, and they measured the light's frequency at the bottom and at the top. As the gamma rays climbed up out of the Earth's gravity, they lost a tiny bit of energy, the same way a ball thrown upward loses speed as it rises. But for light, losing energy means dropping in frequency, and the frequency of a light wave is a kind of clock ticking out cycles. The light climbing the tower shifted in exactly the way it would if time were running faster at the top than at the bottom. The measurement matched Einstein's prediction, first to within about 10%, and later, with refinements, to better than 1%. Time really does run slower closer to the ground, and a 22-meter tower was enough to see it. Now, you might think this is an exotic effect, the kind of thing that only matters to physicists with absurdly precise equipment. It is not. You depend on it every single day, and your life would be measurably worse without it. The global positioning system, the network of satellites that lets your phone tell you exactly where you are, relies on this effect completely. The satellites orbit about 20,200 kilometers above the Earth, where gravity is weaker and time runs faster than it does down here on the surface. The clocks on those satellites tick ahead of the clocks on the ground by about 38 millionths of a second every single day. That sounds trivial. It is not. The whole system works by timing signals to billionths of a second. If the engineers did not correct for the faster flow of time up at the satellites, your position would drift by roughly 10 kilometers per day. Within minutes, your navigation would be useless, and within a day, it would place you in the wrong city. Every time your phone guides you to a turn, it is quietly accounting for the fact that time runs at different rates at different heights. You are trusting Einstein's curve time, not Newton's pull, to find your way home. I want to take you inside this for a moment, because the picture is worth feeling rather than just knowing. Imagine you could perceive the flow of time the way you perceive the flow of a river. You are standing on the ground, and time is moving past you, carrying you forward into the future at its steady pace. But the river is not flowing at the same speed everywhere. Down at your feet, pressed close to the mass of the Earth, the current is just slightly slower, the water dragging, reluctant. Up above your head, farther from the planet, the current runs just slightly faster, freer. You are standing in a gradient, a slope in the rate of time, slower below and faster above, so gentle and so smooth that you have never once noticed it in your entire life. And yet that gentle slope in the river of time is, as I am about to show you, the entire reason you have weight, the entire reason the ground holds you down, the entire reason a dropped cup falls to the floor. The precision of this has reached a point that would have seemed like fantasy to Pound and Rebka. In recent years, physicists have built optical atomic clocks so exact that they can detect the slowing of time across a height difference of just a single centimeter. Lift one of these clocks the thickness of a paperback book higher than its twin, and it will tick measurably faster because it sits a finger's width farther from the Earth, where the flow of time is a hair quicker. Let that sink in. The difference in the rate of time between the top and bottom of a coffee cup is now something we can measure. Time is not a single universal current flowing the same everywhere. It is a terrain with a slope at every height, and we have built instruments delicate enough to feel that slope across the span of your own hand. Every one of these measurements, from the gamma rays climbing the tower in 1959 to the optical clock splitting a centimeter today, says the same thing Einstein said. The closer you are to mass, the slower time runs, and that slowing is not an illusion or an error. It is the deepest fact about gravity there is. There is a consequence of this that I find genuinely difficult to absorb, and I want to leave you with it before we turn to how the slope of time produces falling. If time runs slower deeper in a gravitational field, and it has been running slower at the center of the Earth for as long as the Earth has existed, then the center of our planet is literally younger than its surface. The core has been ticking more slowly than the crust for 4.5 billion years, and over that span, the difference adds up to something you can put a number on. The center of the Earth is roughly 2.5 years younger than the surface, not because it formed later, because time itself has run slower down there, under the weight of all the mass above it, for the entire life of the planet. The ground beneath your feet and the iron at the planet's core do not even agree on how old the Earth is, and the disagreement is real, and it is gravity. Part 11. The straightest possible path. Now I can show you why the slope in the river of time is gravity, and to do it, I need to give you one more idea, the idea of the straightest possible path. Every object that is left alone, with no force acting on it, does the laziest thing it can. It follows the straightest available path through whatever space it finds itself in. On a flat tabletop, the straightest path between 2 points is an ordinary straight line. But space is not always flat, and when it is curved, the straightest available path can look bent to our eyes while still being, in the truest sense, perfectly straight. Let me make that concrete with the surface of the Earth, because it is something you can picture. Imagine two friends standing on the equator, a few hundred kilometers apart, and they both decide to walk due north, in perfectly parallel directions. They are not trying to move toward each other. They each just keep walking straight north, never turning, never steering, holding their heading exactly. And yet, if you watch them from above, you would see them slowly drawing closer together. The farther north they walk, the nearer they get, until eventually, if they kept going, they would collide at the North Pole. Neither one ever turned. Neither one ever felt a sideways push. They walked in straight lines the whole way, but the surface they were walking on was curved, a sphere, and on a sphere the lines of longitude that run straight north all converge at the pole. The curvature of the surface brought them together, with no force involved at all. Now imagine an ant walking on that sphere who has no idea the surface is curved, who believes it is walking on a flat plane. When the ant notices itself drifting toward its companion, it will invent an explanation. It will say there must be some force pulling us together, some attraction across the surface drawing us closer. But there is no such force. There is only the geometry of the sphere, quietly steering two straight-walking travelers into each other. The force is a fiction the ant invents to explain a convergence that is really just the shape of the world. And that, almost exactly, is the situation we are in with gravity. We watch objects fall together, we watch planets curve around the sun, and we say a force must be pulling them. Einstein says no. They are all just following the straightest possible paths they can. It is the shape of space-time that brings them together. The pull is the fiction we invent to explain the geometry. So picture yourself holding a ball near the ceiling and then letting it go. The ball is not moving through space, so all of its motion is motion through time, ticking forward into the future. But, as we just saw, time is not flowing at the same rate everywhere around the ball. Closer to the floor, time runs slightly slower. Closer to the ceiling, it runs slightly faster. There is a slope in the rate of time, and the ball, following the straightest possible path through that slope geometry, curves downward. It accelerates toward the floor. No force pulls it. Nothing reaches across space to grab it. The ball is simply coasting along the straightest line available to it, and that line, in the warped geometry near the Earth, bends down toward the ground. What we call falling is the ball doing the laziest, most natural thing it can in a region of space-time where the shape of time itself tilts every straight path floorward. And here is the inversion that I think will stay with you, because it overturns something you have believed in your body your entire life. When the ball is falling, the ball is the one that is free. If you could ride along on that falling ball, you would feel nothing at all. No force, no pressure, no pull, no weight. You would float, weightless, exactly like an astronaut in orbit, exactly like someone drifting in open space far from any mass. The falling ball is in the most natural, most unforced state of motion the universe allows. It is doing nothing. It is simply following its straightest path. The skydiver, in those long seconds of free fall before the parachute opens, is not being acted upon by gravity. She is free. She is coasting along the geometry, and apart from the rush of the wind, she feels no force at all, because there is none. You, on the other hand, standing on the floor, watching the ball fall, are the one being forced. The floor pushes up on your shoes. Your shoes push up on your feet. Your skeleton carries that push up through your body. You feel heavy. You feel weight. And what you are actually feeling in that very moment is the floor accelerating you upward, shoving you off the straight path you would naturally follow, which would carry you in free fall toward the center of the earth. The ground is not holding you still. The ground is constantly pushing you, accelerating you away from your natural motion, the way the floor of the rocket box pushed up on your feet. In Newton's picture, the falling ball is forced, and the standing person is at rest. In Einstein's picture, it is exactly reversed. The falling ball is free and at peace. The standing person is the one being relentlessly, violently accelerated, every second of every day, by the solid ground refusing to let them fall. This same idea quietly solves a puzzle that has confused people for as long as there have been spacecraft. Why do astronauts float inside the space station? The usual answer, that there is no gravity up there, is completely wrong. At the height of the space station, only a few hundred kilometers up, the Earth's gravity is still almost as strong as it is on the ground. If gravity were really a force pulling things down, the astronauts should feel nearly their full weight. So, why do they float? Because the space station, and everyone inside it, is falling. It is in a permanent state of free fall around the Earth, coasting along its geodesic, curving around the planet exactly as a dropped ball curves toward the floor, only moving sideways so fast that it keeps missing the ground. The astronauts are not weightless because gravity is absent. They are weightless because they are doing precisely what the falling cup does, following the straightest path through curved space-time, feeling no force at all. The space station is just a very large object falling forever, and the people inside it are falling with it, free the entire time. The moon does the same thing on a grander scale, endlessly falling around the Earth, endlessly missing, tracing its straight path through the bent geometry our planet carves into time. I have to warn you about one picture, because it gets this exactly wrong, and you have almost certainly seen it. It is the picture of gravity as a heavy ball sitting on a stretched rubber sheet, making a dip, with smaller balls rolling around inside the dip. It is everywhere, and it is badly misleading for two reasons. First, it explains gravity using gravity. The marble rolls down into the dip in the rubber sheet because the real gravity of the Earth pulls it down into the dip. The picture secretly assumes the very thing it claims to explain, which is no explanation at all. Second, and more importantly, the rubber sheet only shows the curving of space, the dip in a two-dimensional surface. It shows nothing about the curving of time. And as we have seen, for everything in your daily life, moving slowly compared to light, it is the curving of time that does almost all the work. The rubber sheet is a fine place to start a conversation, but if you stop there, you will never understand what gravity actually is. The real curvature, the one that pins you to the floor, is in how fast clocks tick at different heights. You cannot see that on a rubber sheet. You have to think your way to it. And thinking your way to it is harder, but it is the only path to the truth. Part 12. What we still cannot answer. Now I want to be honest with you about a question we have been circling, because I think you deserve honesty more than comfort. We have established that mass warps space-time, and that objects coasting through that warped geometry is what we experience as gravity. But why? Why does putting a large ball of rock and iron in one place change the rate at which nearby clocks tick? Why does mass curve space-time at all? And the truthful answer is that we do not fully know. What Einstein gave us is a relationship written in what is called the Einstein field equation. On one side of that equation sits the curvature of space-time, the bending of space and time, captured in a precise mathematical form. On the other side sits everything that creates that curvature, and it is more than just mass. It includes energy, momentum, pressure, stress, all bundled together into a single mathematical object. The equation says, in effect, that the curvature on one side equals a constant times all that mass and energy on the other side, where the constant involves Newton's gravitational constant and the speed of light. Give the equation any arrangement of mass and energy, and it tells you exactly how space-time will curve in response. And it works. It works with a perfection that is almost frightening. This one equation predicted the bending of starlight, the precession of Mercury, the slowing of time near mass, the expansion of the entire universe, the existence of black holes, and the existence of gravitational waves, and every last one of those predictions has been confirmed. But the equation describes the relationship. It does not explain the cause. It tells you that mass and energy curve space-time, and exactly how much, but it does not tell you what space-time is made of, or why mass and energy should bend it at all. Think of it like a waterbed. If you set a bowling ball on a waterbed, the surface sags, and you can write down a perfectly good equation relating the weight of the ball to the shape of the sag. That equation would work every time. But the reason the waterbed sags is that it is made of a flexible membrane filled with water, and the ball presses down on that membrane. You understand the mechanism. You know what the bed is made of and why it gives. With space-time, we have the equation for the sag, and it is flawless, but we do not know what space-time is made of, or why it bends under the load of mass and energy. We have the law and not the mechanism. This is one of the largest open questions in all of physics, and the people who eventually answer it, who finally explain what space-time really is, and why mass curves it, will be remembered alongside Newton and Einstein themselves. Some physicists suspect the answer lies in a quantum theory of gravity that we have not yet discovered. Perhaps at the very smallest imaginable scales, far below the size of any particle, down near a length so tiny it is written as roughly 1.5 times 10 to the minus 35 meters, the smooth fabric of space-time dissolves into something else, something grainier and more fundamental. Maybe it is built out of quantum bits of information, or threads of entanglement, or tiny loops, or a restless foam of structure constantly appearing and vanishing. The smooth geometry we experience might emerge from that hidden quantum structure, the way the smooth, glassy surface of a lake emerges from trillions of jostling water molecules, none of which, on its own, looks anything like a smooth surface at all. If that is right, then the link between mass and curvature might turn out to be a natural consequence of the rules of that deeper layer. But we do not have the theory yet, and we may not have it for a very long time. While we wait, let me tell you a few things we do know for certain, because they deepen the picture in ways that genuinely shock most people. The first is that mass is not the only thing that curves space-time. Energy does too, in every one of its forms. A box of hot gas weighs very slightly more than the same box of cold gas, not because there are more atoms, but because the faster motion of the hot atoms is itself a form of energy, and energy gravitates. A box full of light weighs more than an empty box by an unimaginably tiny amount because light carries energy and energy bends space-time. In everyday life, these contributions are far too small to notice, but the principle is profound. It means gravity is not really about stuff at all. It is about energy, and mass is simply one especially concentrated form that energy takes. The second thing is even stranger. Pressure gravitates. The pressure inside an object, the very force pushing outward to hold it up, is itself a source of gravity. Newton never dreamed of this, and it has a terrible consequence in the most extreme places in the universe. Far inside a collapsing star, matter can be squeezed to staggering densities, and the pressure needed to hold the star up against its own gravity becomes immense. But that pressure is itself a source of more gravity. The harder the star pushes outward to support itself, the more its own pressure adds to the curvature, crushing it inward. Above a certain mass, roughly 2 to 3 times the mass of our Sun, this becomes a runaway. No physical force in the known universe can generate enough pressure to halt the collapse, because every increase in pressure only deepens the gravity it is fighting. The star falls through its own gravity and becomes a black hole. The very strength it used to resist collapse becomes the thing that finishes it. That is one of the most unsettling predictions in all of physics, and it falls straight out of the idea that gravity is geometry sourced by energy and pressure. There is a way of summarizing the whole field equation in a single sentence, and the physicist John Wheeler put it better than anyone. Space-time tells matter how to move, and matter tells space-time how to curve. Read it slowly, because it is the entire theory of gravity compressed into one line. The curvature of space-time guides every object along its straightest path, deciding how the planets orbit and how the apple falls. And in return, every object, by virtue of its mass and energy, bends the space-time around it, contributing to the very geometry that then steers everything else. It is a conversation that never ends, matter and geometry endlessly shaping each other, the Earth carving a well in the flow of time that holds the moon and sun raising tides in our oceans, every scrap of mass in the universe, quietly sculpting the stage that all the others move across. There are no threads, no pulls, no forces reaching across the void. There is only this endless, silent negotiation between stuff and shape, and that negotiation is what we have always called gravity. And space-time curvature does not just sit there, fixed and frozen. It can move, it can ripple. If you suddenly shake a massive object, a wave of curvature spreads outward from it at the speed of light, a ripple in the geometry of the universe itself. These are gravitational waves, and Einstein predicted them in 1916. For nearly a century they remained purely theoretical, too faint to detect, because the ripples that reach us are almost impossibly small. To catch one, you would need to measure a change in length far smaller than the width of a single proton across a detector kilometers long. Most physicists doubted it could ever be done. And then, on the 14th of September, 2015, at 51 minutes past 5 in the morning, Eastern Time, it was done. Picture that morning. In Livingston, Louisiana, a detector with arms 4 kilometers long suddenly trembles, its mirrors shifting by 1,000th of the width of a proton. 7,000ths of a second later, an identical detector in Hanford, Washington, more than 3,000 kilometers away, trembles in exactly the same pattern, precisely the delay you would expect for a ripple traveling between them at the speed of light. What had reached the Earth that morning had begun 1.33 billion years earlier, when 2 black holes, one about 36 times the mass of our Sun and the other about 29, spiraled together in the darkness and, in the final fraction of a second, merged. In that instant, the collision converted about 3 times the mass of our Sun directly into the energy of gravitational waves, more power, briefly, than all the stars in the observable universe shining together. Those waves spread outward through the geometry of space, washing over galaxy after galaxy, and 1.33 billion years later, a sliver of that ripple passed through the Earth and through those 2 detectors, and was caught. Newton's gravity has no waves. It cannot have them because it acts instantly across all distances. Einstein's gravity ripples and travels and arrives on schedule, and now we have felt it pass. Part 13. Time is the hidden author. I have told you that mass warps both space and time, And I want to drive home the single most important and most overlooked fact in all of this, because nearly everyone misses it. When it comes to the gravity you actually feel, time, not space, is the primary author of the whole experience. Yes, mass curves space as well. The geometry of space near the sun really is bent, and straight lines through it really are slightly deflected. And that bending of space is what produces the extra deflection of starlight that Eddington measured during his eclipse. But the curvature of space is a small effect for anything moving slowly compared to light, and everything in your daily life moves slowly compared to light. A car on the highway is creeping along at a few 100,000ths of the speed of light. Even the fastest machine humans have ever built travels at less than 1% of light speed. For all of these slow, ordinary motions, the curvature of space barely matters. It is the curvature of time that does almost all the work. So when you throw a ball straight up and it rises, slows, stops for an instant, and falls back into your hand, here is what is truly happening. In Newton's picture, a force pulls it back down. In Einstein's picture, the ball, the moment it leaves your hand, begins following the straightest possible path through space-time, and the space-time around the Earth is curved overwhelmingly in the direction of time. The gradient in the flow of time, slower near the ground and faster up high, shapes the geometry so that the straightest path the ball can take is an arc that rises and curves back down. The ball is not turned around by a force. It is tracing the laziest, straightest line available in a terrain whose slope is built out of the changing rate of time. If time flowed at exactly the same rate everywhere, if there were no slope at all, the ball would simply sail upward forever in a straight line and never come back, because there would be no curvature to bend its path. Falling exists because time runs at different rates at different heights, and for no other reason. Let me put a number on how small the cause is and how enormous the effect, because the ratio is staggering. The difference in the rate of time between your head and your feet, over a height of about 1.5 meters, is roughly 2 parts in 10,000 trillion. That is, a difference in the flow of time so small, it is almost not there at all, a few parts in the 16th decimal place. And yet that infinitesimal slope in the rate of time, applied to an object that is moving through time at the full speed of light, produces an acceleration of 9.8 meters per second every second. A push strong enough to pin you to the ground, to break your bones if you fall badly, to hold the oceans down, to keep the entire atmosphere from drifting off into space, and to bend the orbit of every planet in the solar system. The leverage of time is almost beyond belief. A whisper of difference in how fast clocks tick, spread across the height of your own body, produces the overwhelming weight you feel every moment of your life. Now let me take you to the most extreme place this idea leads, because extremes are where you see the architecture most clearly. A black hole is not really an object at all. It is a region of space-time, a place where the curvature has become so severe that every possible path leads inward. We talked about how a falling object follows the straightest path through curved space-time. Near a black hole, the curvature is so total that there are no straight paths pointing outward anymore. Once you cross the boundary, called the event horizon, every direction you could possibly move, every straight line available to you, leads deeper in. There is no outward direction left, not in space, and here is the part that breaks the mind, not in time either. The mathematics of general relativity show that inside the event horizon, the inward direction and the forward direction of time trade places. Falling toward the center is no longer a motion through space that you might resist. It has become a motion through time as unavoidable as the arrival of tomorrow. You cannot stop falling toward the center of a black hole for the same reason you cannot stop tomorrow from coming. It is simply in your future, and the future is not optional. This is also why light cannot escape a black hole, and the usual explanation gets it subtly wrong. We say the gravity is so strong, it pulls the light back. But that is the old language of forces, and it is not what happens. Light cannot escape because, inside the horizon, there are no paths that point outward for it to travel along. Every path, whether followed by a beam of light or by a falling spaceship, curves inexorably inward. The geometry has closed around itself like a one-way street, with no exits and no turning. Nothing escapes, not because something holds it back, but because there is nowhere out left to go. If the dominance of time over space still feels abstract, here is a way to anchor it. The reason space curvature barely matters in your life is that to feel it strongly, you would need to move at a sizable fraction of the speed of light, and you never do. But you are always moving through time at the maximum rate every second of your existence, whether you are running or sitting perfectly still. So the curvature of time has a permanent, unbroken grip on you that the curvature of space simply does not. Even when your body is motionless in a chair, all of your motion is motion forward through time, and so the slope of time acts on you with its full strength, pressing you down into the seat. This is why gravity feels so relentless and so constant. It is not waiting for you to move through space to take hold. It is working on your motion through time, and you can never stop moving through time. You cannot sit still enough to escape it, because sitting still is exactly the condition in which the warping of time has the most complete hold on you that it can possibly have. And these are not fantasies or chalkboard speculations. We have seen these objects. We have caught the gravitational waves from black holes colliding, as I just described. And in 2019, we did something even more direct. A network of radio telescopes scattered across the entire planet was linked together to act as a single instrument nearly the size of the Earth, and it was pointed at the center of a galaxy called M87, more than 50 million light-years away. There, it captured an image of the supermassive black hole at that galaxy's center, a monster about 6.5 billion times the mass of our Sun, ringed by a glowing halo of superheated gas swirling at nearly the speed of light. That image, released to the world, is not an artist's painting and not a computer simulation. It is a photograph. It is a real picture of curved space-time at its most extreme, of a region where the geometry has folded so completely that not even light can climb back out, captured by humans standing on a small planet 50 million light-years away. Every gravitational wave, every bent ray of starlight, every slow precession of an orbit, every ticking difference between two clocks at different heights tells the same single story. Mass and energy curve spacetime. Curved spacetime tells objects how to move, and the thing we have called gravity for 300 years is nothing more and nothing less than the shape of time. Part 14. You have never felt gravity. This brings us back, at last, to the question in the title. Why does mass create gravity? The truthful answer requires a little patience, and one more idea, the most famous idea in all of physics. Mass is a form of energy. Einstein showed this with the equation that everyone has seen and almost no one is taught to feel. Energy equals mass times the speed of light squared. Mass and energy are not two different things. They are the same thing, measured in different units, the way a distance can be written in kilometers or in miles. And energy, in every one of its forms, is what sits on one side of Einstein's field equation, telling spacetime how to curve. Mass curves spacetime because mass is energy, and energy curves spacetime. The motion of hot gas curves it. The pressure inside a star curves it. A beam of light curves it. All of it, every form of energy, bends the geometry of space and time. But notice what that answer does and does not give you. It tells you that mass creates gravity because mass is energy, and energy curves spacetime. It pushes the question one crucial step back, and then it stops. Because the next question, why does energy curve spacetime at all, is one the field equation cannot answer. The equation describes the relationship with perfect accuracy. It does not explain the cause. Perhaps the cause lies in a quantum theory of gravity we have not yet found. Perhaps space-time is emergent, and at the deepest level, what we are calling curvature is really a statistical property of some hidden quantum system, the way temperature is a statistical property of jiggling molecules. Temperature is not a fundamental substance. It is a summary of how fast countless particles are moving. Maybe curvature, too, is a summary of something more fundamental, something built out of quantum information and entanglement that we are only beginning to understand. Or perhaps the field equation simply is fundamental, and asking why mass curves spacetime is like asking why 2 and 2 make 4. Perhaps some truths are bedrock, with nothing underneath them to explain. We do not yet know which of these it is. And I find something quietly beautiful in that honesty, in a theory powerful enough to photograph a black hole and humble enough to admit it does not know what spacetime is made of. There is one more thread worth pulling, because it hints at where this might all be going. If gravity turned out to be geometry, the curving of spacetime, then physicists could not help but wonder whether the other forces might be geometry too. As early as the 1920s, a pair of physicists named Kaluza and Klein proposed that electromagnetism might be a kind of curvature in a hidden fifth dimension of space. String theory, the most ambitious attempt to unify all of physics, extends that idea to 10 or 11 dimensions. None of these proposals has been confirmed, and they may yet turn out to be wrong. But the suspicion that animates them, the suspicion that every force in nature is secretly geometry, that everything in the universe might reduce to the shape of some higher dimensional structure, started right here. It started with gravity. It started with Einstein's realization that a falling apple is not being pulled down, but is simply, quietly free. Think about that apple one more time, because it is where this whole story began. Newton watched an apple fall and asked what force pulled it, and that question led to the greatest equation of his age and ruled physics for 2 centuries. But buried inside the question was a hidden assumption. It assumed that something must have pulled the apple. Einstein looked at the very same apple and asked a different question entirely. He asked, what if nothing pulled it at all? What if the apple is doing absolutely nothing, simply coasting along the straightest path it can find, and it is the ground rushing up to meet it that is really in motion? It sounds at first like a word game, a clever trick of perspective. It is not. It is a complete reconstruction of what space and time are, what motion is, what force is, and what it means for one piece of the universe to influence another. The apple in freefall is tracing the straightest possible line through reality, and reality, near a massive body, is bent. Mass does not create a force called gravity. Mass warps time, and warped time is what we have been calling gravity for 300 years. Now let me show you what this means for every single moment of your own life, because this is the part I most want you to carry away. From the day you were born to this very second, you have never once felt the force of gravity. Not because you were not paying attention, but because there is no such force to feel. What you have felt, continuously, without a single interruption, your whole life long, is the electromagnetic force of solid matter pushing back against you. The weight in your legs when you stand, the pressure against your back when you lie down, the firm jolt of the ground when you land after a jump, none of that is gravity. All of it is electromagnetism. The atoms in the floor refusing to let the atoms in your body pass through them, holding you up, preventing you from doing the one thing you are always, in every instant, trying to do, which is to fall freely through curved time. Gravity is what you feel when you feel nothing at all. Gravity is the experience of the skydiver in the silent seconds before the parachute opens. Gravity is the astronaut floating weightless inside the space station. Gravity is weightlessness, the soft and unforced coasting of an object left entirely to itself. And what we have spent our whole lives calling the feeling of gravity, the heaviness, the weight, the pull, is in truth the exact opposite. It is the feeling of being prevented from following gravity, the resistance of the solid world holding you back from your own free fall. The language of everyday life has it precisely backward. We say we feel gravity. We never feel gravity. We only ever feel the ground refusing to let us fall. So the next time you drop something, watch it closely and let yourself see it the new way. The cup is not being pulled toward the floor. The cup is free. It is coasting through warped time, tracing the most natural path the geometry of the universe allows, perfectly at peace, weightless the whole way down. You are the one being pushed. You, standing there, feeling the floor against your feet, are being shoved upward, held away from the free fall that is your most natural state, by nothing but the stubborn electricity of solid matter. The weight you feel is not the earth pulling you down, it is the ground accelerating you up. And all of it, the falling cup, the weight in your legs, the orbits of the planets, the slow turning of the galaxies, is the same quiet thing. It is geometry, it is the shape of time itself, bending gently around every scrap of mass and energy in existence, including the small and temporary arrangement of it that, for now, is you.